The example problem at hand today is a simple cantilever beam which will be idealized as a shell. Now this cantilever beam is not a standard Euler-Bernoulli cantilever beam. So these are certain basic differences that we are going to take into account. This is not an Euler-Bernoulli beam, and I would like to write this, and the reason is that it is because it's a thick beam. So when it's a thick beam, then you have all other effects such as shear that come into play, and therefore this beam is also sometimes referred to as the Timoshenko beam. Now, the way we would like to idealize this cantilever beam as a shell is looking through its cross section. So this is a one-dimensional image, and now we're looking at the two-dimensional image in terms of this shell. So what you're looking at here is actually the same beam which has been just been blown up in height-wise direction. That means we want to make a planar shell which will have a certain dimension which will be corresponding to the length of the beam as well as the height of the cross section. And the thickness of the shell is going to be given as the width of the beam. So in this case, you would have, according to these dimensions given to you over here, this would become H, this would be L, and the thickness of the shell, the T shell, is going to be equal to B. Now the questions that we want to ask ourselves here, because all the properties are given to us, if you calculate the nu out of this, you will get 0.35. So if you want to ask all different kinds of questions, is how many elements do you need to be there through the width of this element or through the height of this element in this case, when you are using Q4 elements. Now if you remember, Q4 elements are just quadrilateral elements with in-plane behavior. And we know that they cause a certain kind of a behavior under moments which can make it lock. So if you want to see a bending behavior, it is not possible to see it through the standard Q4. So either you can use Q8 elements to have a better behavior, or you can use Q4 elements with higher meshing. So you have to think about, if I am going to use Q4, how many elements do I actually need through the width? The second one is, how do you want to mesh the beam? What would be your strategy of meshing the beam? What are the parts you need to mesh more finely, the ones that you need coarsely, etc. And if you see some kind of an unusual behavior, what exactly is this unusual behavior? So I'm going to now continue and move on towards abacus. And also with Patra and Nashran, we do the same problem. So you see how exactly to solve the entire problem through step by step. But you already know the steps, so I would recommend you to actually work it out first yourself. Get the results for analytically. You can look at some paper or something and find out what the analytical results for the bending would be in case it's a Timoshenko beam. So what would be the shear component that would be added? So what kind of displacements are you expecting at this end of the beam under a certain load Q given here? And compare it to your results and see if you can get closer to it. So let's start with the solution of the example problem of the cantilever beam, which is a thick beam. Now, under general conditions, if we have a certain cantilever beam which is loaded at the end with a load P, then we can quite easily find out the maximum deflection at the end of the beam as to be given as PL cubed by 3EI. So it's easy for you to find this out, and also maybe you remember it from your previous studies. Now, in case of, this is just a bending beam, so we can just write Euler-Bernoulli principles apply here. But if you have a thick beam, then you have additional term given as shear strain, shear stress that comes inside. So there is a shear which has to be added to this equation here, and it doesn't remain as simple as this one. So you can look up a number of papers, of course, which I'm going to show you now. So as I said, if you look at certain literature which is present on the internet, and I'm going to also publish this particular paper, or just put it on the website for you on the blackboard, you can see that there is a use of a Timoshenko's exact solution for cantilever beam analysis. I don't need you to look at more details of adaptive analysis, etc., but just to look at the conditions that have been presented here. The problem definition is exactly the one that we have been looking at. So if you have a cantilever beam, which is given here in this picture, it's a two-dimensional image here with x and y, and there is a load P acting at the edge. It has been assumed here for sure that it is a load Q in our problem example problem definition, but this is a shear load that is acting at the edge of the beam. I will give you some couple of examples later when we start working out this problem, but you can see that the displacement in x and y is much more elaborate for both the directions than just for the one that we just saw analytically for a pure bending beam. So therefore there are some terms that are additional to this which are attached to this problem. You can also look at other sources to get simpler equations just in one dimension. You don't have to pick everything, but it is possible to get the shear term included in it, which gives you a better analysis result or some finite element approximation actually to start with.